Professor Shaheen from the University of Denver. It's about the organic photovoltaics. There are 2 lectures about this.
Well, thank you, everybody. It's certainly a pleasure to be here. This is my second iCamp appearance, thanks to Yvonne, and they seem to get better every year. So luckily, I have 4 lectures to give to you, so we can cover a broad range of topics. And this first part of today will be really a broad overview. I'll give you just a general idea of the devices, the materials, what the marketplace looks like, a little bit of economics. And then later today and tomorrow, we'll do a little more equation-y type stuff and do some more hardcore device physics. But the first part here is largely a lot of pretty pictures. So yes, I'm at the University of Denver, Department of Physics and Astronomy. And about 5 years ago, I used to work full-time for the National Renewable Energy Laboratory, NREL. That's in Golden, and I still retain a contract with them. So I'd like to begin first by thanking all the people who have contributed to the work. And right now I have 4 graduate students, Alex Dixon, Shin Jiang, Ajaya Sikdo, and Brian Appleby. They actually all work at NREL, and some of them are sponsored by my colleagues Joe Barry and Nikos Kopidakis at NREL. So these guys work on projects closely with me, but I work with a whole bunch of other people on a variety of projects, sort of different levels of collaboration, different centers at NREL. And I should thank NSF and most recently the Research Corporation for some funding. I should add that increasingly I'm collaborating with CU Boulder, and I hope that grows even more in the future. First, a little geography, so following on the theme of some of the previous speakers. In case you don't know where Colorado is, I know some of you definitely do. Some perhaps are a little fuzzy on the topic. So let's see, here's California, Utah, here's Colorado, an amazingly square state. Denver is up towards the northern part of the state. And so here's my university, University of Denver. It's just south of the city a little bit. And to give you some bearings, here's Boulder. Here's where Yvonne sits. And then the NREL laboratory is in Golden. And this is about 20 kilometers this way and about 50 kilometers this way. Importantly, you see all the green stuff here. And that, of course, is the Rocky Mountains. And that important aspect are the ski resorts. And these are some of my favorite. Winter Park I go to a couple times a year. Keystone and Breckenridge, all these are about 1 hour drive away. One of my favorites is called Wolf Springs. It's down here past the Salida. So if you get the chance, please stop by. We'll take you skiing. Not this time of year, but maybe in a few months. Just some pictures of DU. So this is the campus in the winter. These are the Rocky Mountains in the background. We've got about 12,000 students, most of which are actually graduate students. Most of those are in the law and business fields. They're not all in physics studying organic photovoltaics, I can tell you that. Here's what it looks like now, a little more sunny, a little more green. To continue with these flashing pictures, this is the NREL campus. This is a new building. That's the research support facility. At the time that it was built, it was the most energy efficient office building in the world. It's zero energy. There's solar panels on the roof. There's lots of energy saving mechanisms in there. Here's a side view of it. So there's about 800 employees who work in that building. If you go above NREL, there's a Mesa and a big table, and there's lots of solar arrays up there that are undergoing lifetime testing, efficiency testing, and whatnot. So NREL is supposed to be the premier photovoltaic laboratory for the U.S. Department of Energy. And I like this photo just because it shows some nice grass, and sometimes you see some rabbits hopping in the grass there. Okay, so I think yesterday we heard a little bit of motivation about economics. I'd like to continue that a little bit. And so first of all, solar energy is growing incredibly rapidly. So every year the growth in the market is about 40% over the previous year. So this exceeds nearly any other market, except perhaps some internet startups. And in 2009, there were 7 gigawatts of peak power that were sold in the world. And at the time, they had projected this sort of growth curve. But actually, the reality exceeded expectations quite a bit. And in 2010, the latest estimates are that number is now at 15 gigawatts. So the total shipped photovoltaics almost doubled between 2009 and 2010. And we seem to be on this curve now, so for 2011, we're on pace for 20 gigawatts peak of production.
That's in the world or the US?
This is in the world, globally, yes. This is per year. This is not the total that's already installed. This is installed per year. So interestingly, the landscape or the, let's say, heterogeneity of the market is changing, of course. And one of the big players now is First Solar, the cadmium telluride PV company. And at the time of this data, they were the largest in the world. They've now dropped to number 2, behind, I believe, Suntech. So these are all basically silicon manufacturers. Most of them are in China. So Suntech, Sharp, Yingli, JA Solar are all Chinese companies. Qcells is the German company. So the interesting part is that cadmium telluride, a non-silicon technology, now has become a really prominent player in the market and has helped to bring the cost down. So speaking of cost, my sort of daily reference for cost, if you go to the homepage solarbuzz.com, you can get up to the date statistics on prices. This might be a little bit difficult for everyone to see, but so on average in the US, the cost last month was about $3 per watt, and that was down 2% over the previous month. In Europe, it's a little bit cheaper, $2.70. Sorry, €2.70 per watt. Now that's the average. The lowest prices that you can get are much better than that. So a crystalline silicon device is $1.8. Multi-crystalline is again 1.8. And thin film is going to refer to cadmium telluride or copper indium gallium disulfonide 6 disulfide. That's approaching $1 per watt. It's $1.40.
That's the cost of installing?
No, so that's on the right. So this is just the cost of the module. So the total systems cost will of course be more. And we'll do this in terms of cents per kilowatt hour. So these statistics are also on the page. You can look up for a residential system for your house. And a typical power would be 2 kilowatts. And this includes a battery backup. So in the night you can still draw power from the battery. Typical cost would be close to $15,000 US. And if you're in a sunny climate, so Arizona, Southern California, this equates to 30 cents per kilowatt hour. We pay roughly 10 cents per kilowatt hour now for fossil fuels. So it's still 3 times as expensive to put a solar panel on your roof as it would to just use fossil fuel electricity. Go ahead.
You spread that over how many years?
Well, the typical lifetime is 20 years, and that gets rolled into another statistic that I'll show in a moment. Energy payback time and whatnot. So these numbers do not have any government subsidy included in them. So if the state or federal government says we'll give you an extra 1,000 or 2,000, then this number will come lower. A commercial system, so you might have a large supermarket or an industrial plant, and then you might want a 50 kilowatt system. This would cost close to $300,000 US. And in a sunny climate now, you reduce the cost to 20 cents per kilowatt hour. And then an industrial system, meaning out in the desert somewhere with really large systems, so let's say 500 kilowatt system, this might cost $2 million and is now 16 cents per kilowatt hour. So this is now almost half of what it is to put one on your roof, and it's getting a little closer to what it is from fossil fuels. Okay, so now I'd segue a little bit into organic PV, OPV. And so this field is considered right now a thin film technology. The films are in fact very thin, a few hundred nanometers. And so it essentially is competing with cadmium telluride or copper indium gallium diselenide. There's a lot of companies in this field right now across the world. I'll just show you a couple. So Solimer is a company in Los Angeles. So they are claiming the world record at 8.1%. In Germany, there's another company called Heliotech. They're claiming the world record at 8.3%. In Massachusetts, in the US, there's another company called Konarka, also claiming the world record at 8.3%. So these 3 companies have the world record. And now there's a 4th one that I don't mention here. It's called Mitsubishi. You may have heard of them. They now claim they have 9%, so they have the world record. So every company has the world record, it's great. But that gives you an idea that the field is moving so fast that the different companies aren't, let's say, communicating with each other. But that's all good news. Here's just an example of one of the Canarca products. So this is maybe about 50, 60 centimeters wide, can be many meters long, and this is produced in this case on a flexible substrate. I'll show in more detail. So you can buy OPV products. This bag is sold by a German company. It's a little briefcase. It has an organic solar cell patch on the side. It's a few percent efficient. It's enough to charge your mobile phone if you're walking outside on a sunny day. If you go to San Francisco and go to one of a few bus stops and look up, you will see organic PV panel produced by Canarca that also can be used to charge your cell phone. There's a little plug there, I'm told, and you can plug in your cell phone. And Canarca is also selling these sort of large area tents made for perhaps a car parking lot, so you can get some shade and also get some solar energy at the same time. Then there's some more creative products that are on the market. If you go to solariv.com, you can buy these little patches that are maybe 15 centimeters in diameter and coat your house with this IV material. Not super efficient. You get a little bit of electricity. It's mainly for aesthetic appeal. Okay, so why organic PV? Why do we want to do this? So cost is the whole ballgame. There are several measures of cost. There are dollars per watt peak that we've just discussed. There is the levelized cost of electricity, which we'll talk about in a moment. But all of those depend on the cost of the materials and the cost of the processing. And where you really hopefully gain in organics is in the processing. And what I'll mostly talk about today are materials that are solution processed. So we take a powder, we dissolve it in a solvent. This can be chloroform, toluene, chlorobenzene. Make the solution, deposit it through a solution coating technique. The one we use in the laboratory is called spin coating. Maybe some of you have done it. You just have a rotating surface, rotating a few thousand RPM, deposit the material on the surface. Most of it goes away, but it leaves a very thin film, a few hundred nanometers, or even a few tens of nanometers of semiconductor film. Now, of course, this is all as opposed to vacuum processing, and you're all familiar with various techniques. One can think about doing a pulse laser deposition where there's a target here, and you hit it with the laser, or in this case with UV, and you put a substrate here, and you knock off target material onto the substrate. Plasma deposition, some sort of sputtering process, same kind of deal. You get a high or medium vacuum, maybe ultra-high vacuum. We have a target, we come with plasma that knocks off target material onto the substrate. So we have these two different worlds. This is done in atmosphere, so under normal conditions. Maybe we've removed some of the oxygen and water vapor. These are done under ultra-high vacuum processes. The assumption is that solution processing in general will be a little bit amenable to large-scale production, a little bit cheaper. But that's a bit of a debatable topic. In fact, one of the companies I showed you, Heliotech, is using a vacuum process, but a little bit cheaper than either pulse laser or sputtering. So we have these two worlds for fabrication. We think this one is maybe a little cheaper. This one is probably a little better in terms of material purity and gives you some freedom in terms of how many layers you can put on top of each other. The issue with solution casting is that it's difficult to put a second layer on top of a first layer because you could wash away the first layer. So you need to be very careful about the chemistry to have orthogonal solvents to allow you to build up layers. Okay, so as I said, mainly I'll talk about this technology in the next couple of days, but all the physics I describe are equally valid for the vacuum processing side of things. So I showed the little spin coating chuck. Here's a picture in our laboratory. There's a 1 square inch substrate. Here's a sort of just aluminum foil bucket that catches all of the solution. Here's an orange solution. This is a polymer, polyphenylene vinylene. It's a derivative of that. Now we do that in the laboratory on a daily basis, but that's not going to work for large-scale production to produce those square meters that I was talking about that I showed. So there are a variety of other techniques. This one is called a doctor blade. This structure here sits a few millimeters above the surface of the substrate, and you take the solution and you inject it into that gap of a few millimeters, and then you simply slide the blade across the surface, and that leaves sort of residual film. And other variants of that, like slot die extrusion, flexographic printing, inkjet printing, screen printing, spray coating, these are all techniques that we can potentially use to create large area. The good thing is that there is a lot of history in these technologies, primarily in the printing industry. So printing of newspapers, magazines, printing of photographic film. So I talked about the company Kanarka. They have a long history that's stemming from the photographic company Polaroid. So you don't really use Polaroid cameras anymore. So that company went into solar cells. And in fact, the industrial plant that once made Polaroid film is now making these solar cells. Let's see. So one issue when you go from small area to large area is you want to mitigate defects in the material. That is a problem that was that plagued or was a problem for cadmium telluride for a long time. They could make very efficient small devices, but when they went to larger area, the defect density was too high and the device performance suffered. Now they're getting better at making those large area devices, and we hope to follow the same path with organics. Okay. In addition to organic photovoltaics, there's a whole field out there of organic electronics, of companies printing transistors for circuitry. And just an example here is a roll-to-roll process. So you've got a roll of some plastic substrate and then a roll that's collecting it, and it goes through the printing process. And here it's printing transistors. In this case, these are radio frequency ID tags, RFID. And this is a very quickly moving technology. So some of the companies working on this, like Plastic Logic, are printing something like 10,000 transistors made of organic semiconductor onto a flexible substrate. So in terms of, let's say, computing power, the organic electronics industry is essentially where silicon was perhaps back in the 70s in terms of the number of devices. But of course, the cost of manufacturing, the speed of manufacturing is much better. And some of the applications can be much different. If you have this very lightweight, flexible, very cheap material, you can think of lots of ways potentially to use that. So for the solar cells, we want to do the same thing. And there's also a small industry starting making equipment for printing organic solar cells. So it's a little difficult to see, but there's a roll in here that has a substrate material, and it's going to roll up and through the material and through the chambers and go through a number of processing steps to deposit the material, maybe do some thermal annealing of the material, and so on. There's a lot of things to be learned between the two fields of electronics and photovoltaics. So a few more slides on economics, and I promise we will get to some science here pretty soon. One of the ways to measure solar cell performance is the energy payback time that we talked about yesterday. So this is energy payback time, EPBT, in years. And this particular study that was presented last summer at the IEEE Photovoltaic Specialist Conference compared a number of organic materials to other thin films. The other thin films are microcrystalline silicon, amorphous silicon. Here's the cadmium telluride. Here's a dye-sensitized device, which I'll talk about in a moment. And these green things are all variations of organic materials, of various polymers, P3HT, with various acceptors like PCBM, or another polymer is PTB1 with PCBM, and I'll talk about those different material combinations in a bit. But the story is, of course, when you see the green bars, they're actually quite small. The energy payback times are in the order of 0.4 years, or about 5 months, as done by this economic analysis. And they actually compared pretty favorably with a lot of the inorganic technologies. Now I want you to take this with a grain of salt. Do you have that phrase in Spanish? Probably a similar phrase. These economic analyses, of course, depend on all the parameters that one puts in, and it would be possible to get much different numbers depending on the degree of accuracy of the parameters. A lot of people are still working on this, but at least the initial data looks promising. To come to this issue of levelized cost of electricity, the LCOE. So we talked about dollars per watt as a measure for cost. One that includes the lifetime is called the levelized cost of electricity, LCOE. And so this takes into account all the factors: the production cost, the efficiency, where on the earth you put the material, the rate of inflation, the rate of taxes, all these things, the lifetime and the degradation. When you put all these in, you get a single number back, which corresponds to, in this case, cents per kilowatt hour. Okay, so we want this number to be close to 10. 10 cents per kilowatt hour would be fossil fuel derived electricity. Well, this study showed that essentially one does not need extremely long lifetimes to have a low LCOE. So the conventional wisdom is that you need a 30-year lifetime to get these low numbers. This study said, no, you don't need quite such a long lifetime. As long as you hit about 10 years, then the slope of this plot flattens out a little bit. And just to go through the numbers a bit, if you have a 5% efficiency device with a 20-year lifetime, then you're at about 37 cents per kilowatt hour. But if you have a 15% efficiency device at a 20-year lifetime, then you're at about 12 cents per kilowatt hour. So that gives you an idea of our target goal for the field is something like 12 to 15% would be sufficient to really compete head-on with fossil fuel-derived electricity. So again, LCOE, that's a good measure of economic performance. Okay, so that's motivation and economics. Let's go a little bit into the materials. There's really a huge variety, almost a zoology of materials and devices for photovoltaics right now. And in 2005, we published MRS bulletin cover, the organic-based photovoltaics. And I'll just go through some of the concepts here that one can envision. So, for instance, one could take zinc oxide nanorods, which are researched here, and embed them in a polymer matrix. The polymer does the light absorption, the zinc oxide nanowires here would transport electrons, and you would make a nanostructured sort of paintbrush or nano brush solar cell. Another type of cell would be a multi-junction cell made of organic material. So I said the company Heliotech is thermally depositing or using vacuum deposition, and that allows them to build many, many layers. So they're making devices of 20, 30 layers, and that allows you to make a multi-junction device that increases the efficiency. The dye-sensitized cell, this has been looked at, of course, for a long time. The invention of Michael Gretzel and group. And in this case, you have, again, a nanostructured oxide, usually titanium dioxide. Coated on that is a light-absorbing dye, usually a ruthenium-based dye. This is embedded in a liquid electrolyte, which acts as the counter-electrode. That's sandwiched between two electrodes, and we can get efficiencies up to about 11% with that geometry. So the one I'll focus on mostly for the next lecture and for tomorrow is the bulk heterojunction device. So this is more or less a single layer device. The active layer is just a single layer. And this is a blend between two components. And typically one component is a polymer, as I mentioned. And the other is an acceptor, an electron acceptor. Usually that's carbon-60 base material. So carbon-60 is one of the best electron acceptors we know. If you put that in contact with essentially any other molecule, it'll suck electron off of that molecule, and you'll get an ionized C60 minus and a positive charge on the polymer that's left over. Of course, there's lots of other materials one can put in this. You can put quantum dots in here. You can put quantum tetrahedrons or quantum rods or all sorts of different structures. But mainly I'll talk about polymer fluorine and some other molecules. Okay, so what are the molecules? I have to give you warning, I'm not a chemist. I can point at some of these pictures and say a few buzzwords, but don't ask me in detail how to make these materials. So I have to buy them or get them from collaborators. So this is sort of a little course through history of organic solar cell materials. The first ones really back in the 90s were based on the phenylene moiety, and they're called polyphenylene vinylines, PPVs. There's a couple different variations of those. The one that has become the workhorse, or the fruit fly of OPV, is poly-3-hexylthiophene. So there's the thiophene, and it has a hexyl group which comes off of the 3 position, hence the poly-3-hexylthiophene. So you'll hear me mention a lot P3HT during the next couple lectures. More recently, the chemists have been getting more creative and mixing two different moieties of molecules. And typically what one does is mix an electron donating structure, such as this guy here, with an electron accepting structure here. And that helps you tune the optical band gap and tune the amount of light that's absorbed in the material. So all of the 8% to 9% devices I mentioned are based on sort of copolymers like this that allow a tuning of the optical properties. And we'll talk about that a lot more in part two. So these are all positive charge carrier materials. They're hole transporting materials. We actually have a much more bigger variety of hole transporting materials than electron transporting materials, but we have a couple. The main ones, as I mentioned, are C60 based. So here's carbon 60. We can put a phenyl group on the side here, and we're going to call this PCBM. And this is the most common electron acceptor. This is also the workhorse electron acceptor. So typically we would blend P3HC with PCBM and make our bulk heterojunction material. Another variation of that is carbon 70. So we put 70 atoms in there. We stretch out the soccer ball, the football a little bit. And this can also make very good devices. We really just have a couple other molecular acceptors. As an example, this TCNQ, this also has a very strong electron withdrawing ability, but it doesn't make very good devices at all. But we can use it as a dopant to dope some of the other materials. So just to give you an idea, and these are all solution processed. We can use the spin coating or doctor blading. And then to go to the vacuum processing world, we've got another set of materials. So these are phthalocyanines. They look a little bit like chlorophyll or some other porphyrins. And we can put a different metal in the group here, in the center here. We can put copper, zinc, we can put titanium, a number of things. And so this has a quite strong absorption in the red, so that's good for solar absorption. This structure is a parylene derivative. And paralenes also have pretty good absorption in the red, and they're also very chemically stable. So these are essentially paint pigments, and you would find them in, for instance, a car paint that could last many tens of years potentially. Some other materials. So this is a triarylamine-based molecule. So what you see or can barely see is a nitrogen with 3 phenyl groups. So that's the triarylamine. Anytime you see that structure, you know it's going to be a good hole transporter. Those are very good transporters for positive carriers, but you can use different sort of configurations to get different molecular morphologies. And again, here's our TCNQ that can also be vacuum deposited. This is a bathocuprene, which can be deposited and also is a dopant for some of these materials. Okay, so these two universes, mainly I'll talk about solution processing. So how do the devices work and what do they look like? So we take, for instance, the polymer and the fullerene. So here's our P3HC, here's our PCBM. We mix those in the beaker as powders. We put the solution in the beaker, stir them at some high temperature for, well, about 60 degrees centigrade for perhaps 10 hours, and then deposit the film. And the film that we deposit would be a mixture of these two, and I'll show some microscope images shortly. But this film is very thin. It's only about 200 nanometers thin. So it's much, much thinner than a silicon device, which is upwards of 20, 30, 40 microns, and it's thinner than a cadmium telluride device, which is a few microns. So this is sandwiched between several different electrodes. Now, of course, we need to get light into the device, get carriers out of the device. So we need a transparent conducting oxide, TCO. So in all these devices, there's going to be a TCO material somewhere. The common one we use is indium tin oxide, ITO, but we have some replacements for that as well. On the other side, we will thermally deposit a metal, or we can do some other ways of depositing that metal. So a typical one would be aluminum or perhaps calcium. We can also do silver. So just I'll give you the cartoon picture of the physics, and we'll go into more detail as we go along. So the cartoon picture is the photon comes in, is absorbed by one of the components, can be either the fullerene, this guy, or the polymer, this guy, but typically will be the polymer. And that creates an excited state, the exciton, right? So we have a bound electron hole pair, very strongly coulombically bound. And in order to harness that energy, we have to dissociate that exciton into free carriers. So that dissociation process happens only at the interface between the two materials. So we need that exciton to diffuse around in the three-dimensional lattice, find the interface, and then undergo an ultra-fast charge transfer process so we get electron on the accepting molecule, which is the C60, leaving behind a positive charge on the polymer. So now you've got free electrons in holes, and at this point the device looks a lot like an inorganic device. You've got a field distribution in the device. The carriers are subject to electric fields and to diffusion, and they can then migrate out of the device. And everything goes well, the electron would go towards probably the aluminum, the hole would go towards the TCO material because that is a higher work function material. And once the electron has gone to the one side, the hole to the other, that's the equivalent of one charge passing the whole device, and we're able to capture the photon into an electron. So that's the cartoon picture. Of course, we'll go into much more detail. Now, if along the way that one of those carriers runs into the opposite sign carrier and recombines, then we obviously lose that power that was gained. Okay, just a technical point. I just want to point out that we can make these devices in two different ways. What I just described is called we would call a normal device. In this case, the ITO is the positive electrode, so holes go essentially down in this picture, and electrons go up towards the negative electrode. So we can look at an energy band diagram and get a little idea of why that might be. So here is energy, vacuum level would be up here. These are all negative, so all the energy levels are negative. And the ITO is fairly far from vacuum. What we do is cover that ITO with another polymer. And this polymer is called PSS, or just P. And this is essentially a very conductive polymer that alters the metallic properties of the ITO. So both of these sit pretty far from vacuum. And if we use aluminum or probably calcium, that sits very high to vacuum. And now you can see that we've aligned the orbital levels of the material. So the donor is the polymer, the HOMO is the highest occupied molecular orbital. So this is the band upon which the positive carriers would migrate. Here are the positive carriers. And then the LUMO, the lowest unoccupied molecular orbital, this is where the negative carriers will be transported on the fullerene. So this is roughly the lineup or the alignment of the structure. So you can see electrons will like to go that way, holes will like to go that way. Now, for practical reasons, we can invert that. So we can have holes going towards the metal, electrons going to the ITO. The way we do that is to insert a buffer layer here of some oxide. And actually the best oxide we found for that, or one of the best, is zinc oxide, which sits at minus 4.2 electron volts. This essentially blocks any of the holes that would come from the polymer. This process is blocked, and you get electrons coming this way instead, and then the holes are free to go out the other side. Now what we do is deposit silver, and normally silver, if you look in the handbook of chemistry and physics, silver has a work function close to that of aluminum. But in reality what happens is it oxidizes a little bit, you get silver oxide, and this work function is now further from vacuum, close to the donor HOMO level. So now we flip the device around. The advantage is now we have a chemically stable device. Since calcium oxidizes very quickly, this device is not particularly stable, and one would need to do more effort to encapsulate it from oxygen so that it doesn't oxidize. Okay. So to go into slightly more detail about the operation of the device. So we have our polymer and our fullerene. We can draw a band structure for each one, a HOMO level, a LUMO level. Those are electronic bands. So what happens is we come in with a photon to excite this exciton. Now the exciton can be envisioned by a hole and electron that are coulombically bound. And that means that the band structure dips in a little bit there. So there's a coulombic attraction, and so the energy difference between this positive polaron, we'll call it a polaron, and this negative polaron, it's a little bit different than just the single particle energy that would be there without the opposing species. Right? So these two are bound a little bit, and that energy of binding is called the exciton binding energy. So that keeps the two stuck together. But if we do diffuse that exciton interface, we can transport the electron across the interface, and we'll talk about that in a moment. And then we have the hole on one side of the mixture and electron on the other, and then through both diffusion and drift, we can drive them away. So this process of charge transfer happens really on a very fast time scale. In fact, it's called ultra fast. And it's been measured around 45 femtoseconds for that process from the polymer electrons being injected into the fullerene. This actually competes with natural photosynthesis. So natural photosynthesis, you would get charge transfer rates of 100 to a couple hundred femtoseconds. So this is actually faster than most natural photosynthetic processes. So once the electron is on the C60 on the fullerene, the back transfer rate, which would be a recombination process, is much, much slower. This rate is about 1 microsecond. Okay? So you've got 10 to the minus 6 here, you've got about 10 to the minus 14, so you've got 8 orders of magnitude difference in the transfer rates in the forward versus the backwards direction. So that is what really makes possible the operation of the organic solar cell and gives you a very stable charge separated state. That gives you a lot of lifetime for the carriers to migrate out of the device. I'm going to point out again that this active layer is very thin, it's just a few hundred nanometers. And the organic molecules have such a strong optical cross-section that within 100 or 200 nanometers, they can absorb about 90% of the light, at least at their optimal wavelength, at the peak wavelength. So an optical density of about 1. Okay, how are we doing for time? I think a few more minutes, we'll wrap up section 1 perhaps.
Yes.
Yeah. So just to give you an idea of what these things really look like, we can do cross-sectional transmission electron microscopy. These were done at Sandia National Lab by Julia Shu, who's now at Dallas. So in this case, we physically break the device and we encapsulate it in an epoxy so that we can do that. And just do an edge-on TEM, and you get an idea. Here's the glass substrate, here's the indium tin oxide, here's the zinc oxide. This is an inverted device. And in this case, we have a mixture of P3HT, and we actually put in some zinc oxide nanoparticles, which have very good contrast in the TEM microscope, so you can see a little better the domains of the structure. And then here's some P dot on top and the silver. I think the next image is a little bit better. First thing you notice is that it's not this perfect uniform mixture that I showed in the cartoon, that there's a lot of heterogeneity in this structure. So the ratio of the blending between in this case, the zinc oxide and the polymer can change throughout the depth of the film. So that's a problem, right? We would like that to be homogeneous and somehow optimal for charge transport. So that's one of the issues we'll have to overcome. Scale bar here is 100 nanometers, so this is about 250 nanometers thick. We can also look just top down on the image and look at how the polymer and the fullerene are blended. So here is the P3HT and the PCBM. So what happens is the P3HT has a very strong tendency to pi stack. Pi electrons will drive it into a ladder configuration. And it's not truly liquid crystalline, but it follows some of the same organizational principles as liquid crystal. And it forms these nanofibrils. A little bit hard to see, I imagine, on this projector, but what we get are these nanofibers, which consist of sheets of this polythiophene that are stacked up first in this direction, and then in this direction to form the lamellar fibers. Right? So there's maybe 10 or so that are stacked this way, and then they go that way. And these fibers can be many nanometers long. In fact, can be a couple microns long if you grow them intentionally to do that. So this structure yields a very good efficiency. So if you hit this with the right frequency of light, so something around 500 nanometers, about 90% of the photons get converted into electrons. So somehow this morphology is really good for extracting carriers. But note that it's not perfectly uniform. You've got regions that are darker and lighter, so this mixing between the two is not completely homogeneous. Again, a problem we have to deal with. I should mention that this work was done by a colleague at King Abdullah University of Science and Technology around Malaysia. Another thing we can do is distinguish between these two molecules, and we can aim at that sulfur molecule that's on the thiophene. So we can use energy filtered TEM to hone in on a given, or to focus in on a given atomic species. So if we look at sulfur, we're basically looking at just the polymer. And what you see is, you see a distribution of the polymer that forms some kind of periodic structure. Now we have to do some image analysis on this, and some of the optics experts can hopefully help us with this. But we think there's some sort of structure in here that is not just completely random mixing of the material. And that structure changes depending on how you process the material, and what kind of side groups you have on these different materials. We'll talk about that a little while later as well. One more sort of spectroscopy we can apply is AFM, atomic force. And we can look both at the topography, just getting the surface structure, and also we can do conductive tip. So C, conductive tip AFM. And what we find actually is that there are very large variations in the photocurrent across the surface of the film. Sorry, not photocurrent, in current. So in this measurement, we take the AFM tip, we bias it at a couple volts, and we just run it over the surface and measure the current. Current is measured in picoamps. And we see some spots here that are close to 30 picoamps and others that are about 25. So we have actually variations up to 30% across the surface of the film. So we have a lot of work to get this to be a nice uniform distribution of current that we think we would want for the material. So that just gives you an idea. Okay, a little bit about the devices, and this was covered yesterday. If we characterize the device, we apply a range of voltages, we measure current. Now in the inorganic community, they put the power producing curve in the first quadrant, so the curves go like this. Just for tradition and to be different, the organic community works down here in the fourth quadrant. I guess depending if you're an engineer or a physicist, which gives you positive power. But so we tend to operate down here, and I think this was covered yesterday, obviously doing a nice sharp curve. The fill factor is a measure of the sharpness of the curve. If you multiply the fill factor times the open circuit voltage times the short circuit current, that gives you the power that is generated. If you take the power generated by the optical power in, one gets the efficiency. Okay, so just an example curve. So if we mix these two materials, P3HT, PCBM, and what we do is called a slow dry process. So we make the film, but it's in a very high boiling point solution of orthodichlorobenzene, ODCB. And if you just cover it with a petri dish, there is a partial pressure of solvent that is built. And it takes a very long time for that solvent to eventually dry. It can take hours, can take days. If you do that, you get the nanofibers that I showed before. And that gives us some of the best device efficiencies from these materials, which is about 4%. So in this case, it's a 3.7% device. We have an open circuit voltage of about 0.6. So that's this point here where the light curve in red is crossing the x-axis. Short circuit current is 9.3 milliamps, so that's this point here. And about 10 or 11 is a little better value we can get. And then the fill factor is the sharpness of the curve, 65%, for a total efficiency of about close to 4%. This is not the world record device, right? I said 8% is the world record. But that's about the best one can do with these materials. If you go in the literature, you'll find something a little bit higher. Okay, I think I will just do one more slide on this section, and then we'll take a pause. So if we want to compare the inorganic devices that we talked about yesterday and the organic devices, there's a couple differences. So an inorganic device, we're going to use some vacuum processing, sputtering, or E-beam deposition, or pulse laser deposition. And we're going to deposit the atomic species with a certain mixture, a certain morphology. So there's morphology at different length scales. There's sort of a local nanoscale morphology. There's also a long scale morphology in terms of how big the crystallites are, if it's a polycrystalline or a single crystalline. All these morphologies determine the physics of the device, how the charges flow, what the field distributions are. And those physics, along with the atomic properties, the band structure of the atoms, in the end will give you a power efficiency once you hit it with light. We have a similar diagram for organic or molecular semiconductors, but in this case, instead of the atomic configurations, we have molecular structures. So that gives us another tuning knob, so we can design molecules that give you different morphologies in addition to the process parameters. So that's maybe a good thing. Now we have maybe a bad thing. We've introduced another step in here, which is the exciton. So in these devices, of course, you hit the photon into the device, you get direct production of carriers, and then you go down the stream. Here we've got excitons that have to be dissociated. So that's another constraint on the device. But once you do dissociate those excitons, you get electrons and holes that are subject to the same physics as we are up here. And then it's now molecular band structure, molecular band energies that give you the power conversion efficiency. So we have maybe some advantages and maybe some disadvantages down there. So, I think let's wrap up part one, and we'll continue after the break.
Okay.
Yep.